All right, so for video editing purposes, I will say welcome back to part two of free stuff. Last week actually wasn't so much about free stuff. Last week we mostly focused on, well, there's this idea of the duality of data and functions. So data and interfaces, the interpretation of data, and how we can kind of move from data to functions. We call that the church encoding. So we could take data structures like Booleans we started out with, or lists, or options, literally any algebraic data type, any combination of immutable sealed traits and case classes, and represent them as functions instead, as lambdas. Though for Scala reasons, we had to use traits in order to simulate polymorphic function types. But it's pretty cool that you can do that. Not necessarily immediately valuable. It tends to make the code weirder to read generally, but it does maybe open our brains a little bit. And we sort of showed that data and functions are isomorphic to one another. They're essentially the church encoded form or an ADT. They're both just as good as one another. Theoretically speaking, performance-wise, they might have different implications. The ease of use might have different implications, but in terms of what you can do with them, you can do the same thing. Yeah. And let me know if you can hear a loud, repeated hammering, because there's some construction, and then I'll shut all my windows. But hopefully Zoom cancels that out. All right. Let me just make sure anyone said anything. Cool. So yesterday we went from data to functions. And then at the end, I tried to sort of show the other way of going from functions to data, but I didn't quite leave myself enough time to do that justice, or really to explain sort of in a small step way what free structures are with simple examples. I kind of bit off this really big, gnarly problem to show a case where using them can be beneficial. But I think it's probably worth breaking that down into smaller steps so we can first have a clear understanding what it even means to be a free structure. Maybe it won't seem so useful right away, but then once we get that understanding of what they are, we can then talk about use cases and patterns for them. Does that sound like a good plan?
Sounds like a plan.
Okay, amazing. So yes, I'm assuming if you're in functional programming, you've probably heard of a couple of free things, like a free monad, like a free monoid. You probably haven't heard of a free functor, but we'll get to that. Really, these are the data versions of bundles of functions, essentially, which we call traits, right? Traits are sort of bundles of different methods. And these free versions are the datafied versions of functions. And let's look at what that looks like. Let's take a look at what that is. Starting off with maybe the simplest of the type classes that there exists. Okay, there are simpler ones, but monoid is the simplest, interesting one, perhaps. So yeah, I will allow Copilot to help me out here, but then I will change some of the words to, I guess, identity and combine. Combine. Okay, and I'll teach IntelliJ. No one knows what it means. It's just that one wants me to rename the file. No, thank you. Okay, so a monoid is this is the type class representation of a monoid in Scala, where we basically it's a bundle of related functionality, and we tend to represent these as traits, but really you could also represent them as monoid case class. We just need there's some type A that we have a bundle of related functionality for. We have this identity function, or this identity value. It's just a single value of A, and then we have a combine method. So really, it's just a bundle of related methods for some data type A, and we could represent that with the case class, but it tends to be represented with a trait. So same deal, really. But yeah, there's nothing real magical about this. It's just a way of bundling together some functionality that's related. And let's talk about some concrete examples of a monoid, because it might seem weird if you don't know what this is in the abstract. But you probably know a few monoids already. For instance, the addition monoid, which I will let Copilot just do for me. Yes, there we go. So the addition monoid looks like this. It's defined for integers. So integers form a monoid where the identity element is the number 0, and the combine operation, this associative binary operation, is addition. Cool. And so yes, we said a monoid had to be one arbitrary value of a set. So in this case, the number 0, and then a function for combining two values of that set into a third value. So smushing them together, a binary operation. Binary meaning 2, takes 2 values, outputs a third value. There is one more related feature of these type classes, which they generally come with laws, which while we cannot directly encode these, in Scala, we can usually have test suites that make sure the laws hold. So really, if we have these two tools, the laws tend to be combinations of those tools and sort of equalities based on how you use them, which sort of define their meaning. So the laws of a monoid are that if you combine identity with A, you get back A. And it doesn't matter which way you do it. If you combine A with identity, either on the left-hand side or the right-hand side, these are called the left and right identity laws, respectively, you will get back the other side, which is obvious with addition. That's no matter what you add 0 to, you're always going to get back the other side. 5 plus 0 is 5. 0 plus 5 is 5. And that's if you replace these with 0 and combine with, add. That's kind of obvious here. But the cool thing is that this works with more than just addition. It works with many types. So there's we can do one for implicit, val, Boolean conjunction. Let's do conjunction, fancy word for and, the Boolean conjunction monoid. So with this, if you have double ampersand, anding together as your binary operation, then true becomes the identity element, because true and true equals true, and false and true equals false. So that true is not really changing. If you ampersand on the identity element here, it doesn't really change the value of the other side, which is kind of neat. And there are many monoids. Some types have multiple monoids. For instance, there's also a multiplication monoid. Implicit, there we go. The only problem is, so yes, there's a multiplication monoid. So let's first look at the implementation, which is that, yeah, it's with multiplication. The only difference is the identity element becomes 1 in this case, because 0 would make everything else 0. That is not, do you know the word for that? That is another sort of special term. If there's an element that sort of just crushes everything else, is this a void or black hole type value, like 0 is under multiplication. Not sure if anyone knows that fancy word. Maybe it's called a 0. The eigenvalue. I don't know. That sounds great. Oh, any number such that a given matrix minus that number times the identity matrix has 0 determinant. I don't know what that means at all, but I like the word eigenvalue. I'm not sure if that's correct, but that sounds good to me. The only problem with this right now is that because we're using implicits to define these, we're going to get ambiguous implicits if we have these both here. But so I'm just going to stick to addition monoid for now. And there are many others for these. Let's just do one last one, which is the implicit val string monoid. This is one that has just one instance here. Maybe there are others, but I think just one. The identity element's an empty string. And if you concatenate an empty string before or after another string, you're just getting back that other string value. So that's what a monoid is. In case you didn't already know what a monoid is, it's a weird pattern of functionality that exists in many types. So type classes are always a little weird to explain because they're not just a type. It's not just int is not a monoid itself, but int can exhibit monoidal behavior. I don't know how they have all these fancy ways of saying this. A monoid closes over int under addition or something. There are all these fancy ways that mathematicians phrase this that I don't really understand how to parse. But the point is, to phrase it into words that I understand, it's a pattern of functionality that involves some type and some combinators and constructors, which is best represented by a type class, because then you could sort of identify special values as well as functions. If it were just a trait that was inherited by something, and so if like maybe say int inherited this, there was some type self and you took self or whatever, then first of all, we have to extend int, which we can't do because it's part of the standard library. But also, we couldn't then add an identity element to that because these would have to be methods on the elements of int. And so calling like 10.identity would be a pretty weird thing to do to get out like the number 1. So yeah, just another reason why we use these weird parameterized traits as a way of having a bundle of functionality that describe this pattern. Okay, great. So that's what a monoid is. And we're going to use this relatively simple type class to explore the idea of free encodings by starting with right here, number 1, the free monoid. So we're just going to start off mechanically how to build a free monoid, and then we'll kind of talk about the implications of it afterwards. But we can't do all of that at once. So we're going to start with just forget about why this is useful or even why this is the free monoid. And we'll talk about how to mechanically create a free structure for any trait really, or type class generally. Okay, so we're going to start by making a sealed trait and calling it Freemonoid. And we're going to give it a type parameter. We're going to make it covariant as well. And then what we're going to do is we're basically going to go through all of the methods of the trait. So I'll list them out here. And we're going to, for each one, define case classes or case objects for these methods. And that will basically sort of be an AST for that, that interface. So we're going to build sort of a data type that represents the idea of calling that method. And as a second rule here, whenever our a method involves a call to the sort of the type that it's parameterized by in this A, so whenever the A is used as a parameter, whenever we are referred to recursively, I guess it's not really recursively, we're going to replace it with the free monoid structure. I need a better way of phrasing that, but we'll take a look at what that means as an example. I'm not sure the best way to describe that. So let's start out with identity. So we're going to take identity and just create a case object for it because it has no parameters. So we're going to say case object identity, and this is going to extend a free monoid of nothing because it has no A values inside of it. So that's sort of the data representation of this function. It's pretty simple. For the next one, we're going to have a case class because we have 2 arguments, and I'm going to call this combine. And A1, because we are referencing the A that is our parameter, instead of just saying A here, this is kind of what I mean by the second point, we're going to replace it with, I guess, an inductive call. So it'll be free monoid of A, and A2 is also free monoid of A, and this will extend a free monoid of A. So those are the first sort of 2 steps, creating this AST that basically directly mirrors the interface. Whenever you have a reference to the value here, you are going to not just have the value A, but reference inductively, recursively, the type itself, the free type that you're constructing. And then lastly, we're going to have a special carrier node, a little sidecar value that's going to let any A value enter this free monoid structure and ride along and be a little passenger on the free monoid express. Because if you think about what we have so far, constructing these free monoid values, all we could really do is create identity values. This is kind of the base case, and then combine identity values, because that's the only base case that we have. So we have this inductive recursive case of the combine. So we can only make these sort of like branching tree structures that end in identity. This is the only leaf node of this data type. And that would be kind of pointless because especially as we know, based on the laws, whenever you combine anything, identity combined with some other element A is always equal to A. So basically, no matter, all these trees are going to really represent identities. If you combine identity with identity, you get identity. And if you do that with lots of combinations, you're still getting identity at the end of the day. So what makes these free structures free, what makes them what makes them interesting is that you can take some other value that may not itself be a monoid, but it gets to become a monoid by riding on this monoid simulator. So we need that entryway. We need that sort of sidecar, the little seatbelt that we can put in another value. So I'll just say value here. And this is going to have a reference to A that is not inductive or recursive. So this is the third step, that special carrier node of our tree. Okay. And that's basically a free monoid, or one representation of it, the clearest representation of it. There may be some problems with it we can discuss. But what's very interesting about this is that we can put any value in here that may or may not be a monoid, and then we can combine it with other values that have been lifted into the free monoid and combine these with identities. And we basically get the structure of composing monoids for any value A. So that's sort of, you get the monoid for free for any value is the idea here. And we're gonna do some more things with this. But first, the interesting thing would be to run this, to fold over this free monoid structure. Yesterday we talked about, yesterday in Zymposium terms, last Friday, we talked about folds a lot, so I'm not going to get into too much of that, but basically we're going to interpret this structure, extract the implementation, the information from the structure. And so what we could do is we could say fold, and we can do the following. We can say basically, well, what is this? How did we define the structure of fold the other day? We had sort of a mechanistic way of deriving folds, just as we have this mechanistic way of creating free structures now. And it was basically to go through the cases of our data type and look at their arguments. If they had arguments, they might go here, but if they don't, we're basically going to some summary element. So identity has no arguments, so it's just going to be a summary element. Combine has two recursive elements, so it's going to look like this. And value has one argument A, and so that's going to go like this. So we need three arguments to our fold, which represent these functions or just values that basically mirror all of the information stored inside of our structure here. So I'm going to say if identity, that's going to be some value, some summary value, I'm going to call it Z for now. And then if combine, we need a function to combine two Z's. And then if value, if this pure value thing, we're going to go from A to Z. And then we can take ourselves and match in ourselves and implement this method, self match. So if identity, we're just going to use this value. If combine, we're going to call if combine, recursively folding either side. And if the free monoid is just the value case, we're going to say if value. And maybe I'll import free monoid here so we don't have to keep referencing that. Make it a little clearer here. Okay, let me break that down into different lines so we can see everything. Okay. So now what we have here is a way of combining, of sort of interpreting our free monoid into a data structure. So let us quickly use this fold method with an example and walk through this. But first, I'm going to add some other methods. I'm going to add a plus plus method, which is going to take another free monoid of A, free monoid of A1, and it's going to get us back a free monoid of A1. And we're going to combine these things. So we can just say free monoid, we already have it combined, self that. We can do this for now. We could also, if we wanted to, follow our laws a little bit and be a little clever here, even though we aren't really a real thing yet, we're just this weird data type. And we can actually match on this stuff and say, okay, if either of these sides are identity, we're basically writing the laws here. Identity and self. In any other case, self that, we're going to do combine. But this implementation of combine basically implements these laws. So identity A is A, or A where's mine? There we go. Cool. And then the last one is just combining them. Sweet. So that's a fun optimization we can make. Okie dokie. So now let's actually use this in an example. Okay, so let's see. Let's say we have some kind of person, and they're going to have a name, string, and an age, int, and I'll have me. Hopefully it makes me. Oof. No, not like that. Person. There we go. I'm not 28, but I'll accept that. Adam, I don't know if Adam's 29, probably. And then we'll do John too. There we go. Very accurate. Cool. And now what we can do is we can combine these things into a free monoid. So I can say, let's combine me. So free monoid. Oh, there we go. So we're just combining all of us. All three of us are going to be combined together. Great. And let's take a look at what this looks like. And as we see, it's just a bunch of these like nested combine nodes. So it's this weird tree structure that represents our AST. Not surprisingly. But what we can also do is we can combine these things with Freemonoid.identity if we wanted to. And if we see what happens here, it's going to be the same thing because we implemented our ++ to forget about identities, which is kind of nice. But now we can run this. So let's call fold and make a decision. Let's fold this into an integer. So if it's the identity element, we'll choose 0. We'll do addition otherwise, and then we will take the person's age. So we're basically summing our ages together here. So summing the ages of all the people. So it should be 87. 87. Yay. Okay. So we can build this structure and then fold over it. Cool. Where does the monoid part come in besides the fact that it sort of mirrors the monoid structure? Well, if we come up here and we look at the fold method, we can actually notice that the combine and the identity methods here, if you look at these signatures, these are essentially the signatures of monoid, which isn't surprising because we built this fold structure by looking at the structure of our sealed trait, which we built by looking at the structure of our monoid trait. So it shouldn't be surprising that these things line up. We kind of round trip back to the beginning. So another way of writing this fold method, which is actually something you'll often see on these fold structures, is something called FoldMap, which is essentially the same thing, except it starts with this if value thing, because this if value, this A to Z function is not part of our monoid interface. This is just a way of sort of dealing with this value that we let, pretend to be a monoid for the day. It's time for it to actually enter. We have to explicitly turn it into a real monoid. So we still have this as a first argument. And then as a second argument, we have an implicit monoid instance. Monoid of A. Oh, sorry, of Z, the thing that we're turning our value into. Because this is basically a monoid of Z. This is basically an ad hoc monoid instance for Z that we just happen to be passing in as values instead of as a convenient bundle of those same values. It's really all a type class is. And really, we can implement this using our other method. So I could copy paste the implementation, but really it's monoid.identity, monoid.combine, and then combine, and then if value, right? That's our other implementation. And so, yeah, I could inline this, I guess, or copy paste it. But it's really, this tends to be the method that you will see implemented. Maybe I will actually remove fold and do it in terms of this. And then I'll just say monoid.identity, monoid.combine. And then I can remove this, this fold, change it to FoldMap. And then I get to delete everything except for if value, because now those same arguments are being shuffled along as implicits. So it makes it maybe a little clearer. Great. So this, if you've ever seen the FoldMap method, it's basically doing what we just did before. It's folding over the structure, but because these free structures tend to represent the sealed traits that's derived from a type class, instead of passing along all those arguments to fold, we can just use the type class directly. Though, because this free structure allows any value to pretend to be a monoid, there might not be a monoid instance for A. There, of course, could be one, and then we can just give the identity function for this, and it'll go from A to A. But because it may not be one, like person, we don't have a monoid for in this case. But if we called FoldMap, and we just give it a way of going from a person to an int, it can then find, theoretically, the monoid instance for int, though it cannot find that currently because I probably didn't make it implicit or I've deleted it. Where did it go? Object monoid, maybe I need to give this a type. There we go, okay, yeah. It may have compiled, but IntelliJ didn't know what it was. So now I can run the same function and it will work just the same because it's literally doing the same thing. This is just a little more of the pattern that you'll see. I will take a brief moment to ask if there are any questions or thoughts or anything else, Adam. I've been going probably too fast for too long.
No, I think that was all really good. I think one thing we were talking about a little bit in the Discord is the similarity of this to just the general concept of that declarative versus executable encoding. Like, I think there's a little bit more of maybe like a layer of disguise here, because like in a way you could think of it, I think almost as like there are two transformations. You're like, one, you're going from like a this like trait, this like type class representation to a like data type representation. So this is kind of just a trait to a data type. And then separately, there's like, okay, let's say I started with a data type that just had like questions for like these like operators. And then I just like did the thing we always do with these declarative encodings of I replace those questions with just data types that like case class essentially that like describe each of them. And that's really like what you've like done here. So I think if you've like done one of these just general declarative encodings, whether it's been for like Zio that we've done, or like I think we did one for a parser, or really you could do it for almost anything. And I think that's what we're going to see when we do some of these other examples of like, look, if the method is map, then give me a map case class and take the things that go into that map and put them into the case class. And once you do that, then you kind of have this like, okay, you have this thing and you've got to interpret it somehow. This like FoldMap is basically like a executor for like this like declarative encoding we've created. And the fact that it takes a function is one way of kind of expressing that we could have like different ways of executing. But that's, I think, one other maybe way of thinking about what we're doing here that relates to some of the stuff we previously talked about.
Yes, if anyone has seen the Zio from Scratch series, we basically do the same thing, except we do not start with a trait. But if we did start with a trait, Zio of let's just say A, well, we know we have like a succeed method for these Zios. If Zio were instead a type class, right, this would bring us to a Zio of A or something. Or actually, oh, this would have to be a little different because it's a parameterized type. So it might be a little wackier here.
Yeah. Well, or I mean, maybe one way you could show that is like with the monoid, like maybe we could do like a monoid like case class or something, or just, right. And we move the kind of identity to being on the object and move the combine to being something that takes one of these monoid likes and another monoid like and gives you back a monoid like.
Yeah, I think I could have done this whole thing by saying like, well, we want a way of getting the identity element. Just make that a function. We're going to get a monoid like.
Yeah, and start by making that like a question mark, because that's like.
Exactly. So this would be a monoid like of nothing. Question mark, question mark, question mark. We know that we want that constructor. Like that's what we did in the world of Zio. And then we knew that we wanted a combinator plus that took, basically the same function, A1. So we tend to start with interfaces when we talk about the Zio world instead of type classes. So it's going to take another monoid like of A1 and return a monoid like of A1. And this is basically what we did. We started with these question marks and then we just, all right, let's just express this as sort of in sort of a bootstrappy cheating style as just a syntax tree that represents that exact method call. So I would say monoid like dot identity and make a case object identity, right? Identity, which extends monoid like nothing. And then same for this. I'd be like, okay, let's just make an AST, just a node that represents the idea of combining. So we'll have this and that. This is exactly the process that we took for the Zio from scratch process. Extends monoid like A. I think that's confused, but that's okay. Why is that confused? Monoid like any. This. Oh, because A1 is not a super type of A. Okay. And really, we've gotten the same exact thing that we have here. I mean, I had an extra optimization step here, and I didn't make the def identity method here, but I certainly could just by saying identity and then saying this is a free monoid of nothing. So really, it was the same series of steps, just from a different angle. We started with a type class representation instead of with Zio. We kind of started with maybe examples of calling the API. So we started with syntax and semantics, and then changed those stubs into sort of just being nodes, and then interpreted them later. But it's really the same. It's really just the same exact pattern.
Yeah. And I think maybe another thing is like this FoldMap method. I think in this case, the structure is like so simple that like you probably don't need anything other than the FoldMap method. But like what we're creating is just this big data type, just like with like the Zio example we saw, or really any of these declarative encodings. And so we get to just look if we want to, like, I mean, maybe it's even good, like if you want to just do like a print line on one of these like free like monoid things, and like we'll see. It's just like, I mean, if we have too many of them, it's just going to be a big case class, and it's like not going to like look that pretty, but like it's just a case class, and we can do whatever we want with it. That FoldMap method is going to give us like a nice way to do like the vast majority of things we want to do, but it's just a thing that we can look at and we can do whatever we want with. And so we could add it up, we could pretty print it, we could do whatever we wanted to with the structure.
And if we imagine that maybe the actual summarization, like when we actually interpreted this into a monoid, we could pretend that, say, that monoid's combine method, let's say, was for whatever reason was really slow. The real monoid we're interpreting this thing into is really costly. What we've gained by doing it like this is that we are able to also statically make some optimizations. So before we've actually done anything with our real monoid, we can cut out these steps of combining. Every time we combine with an identity node, we get to erase that. We're not doing combine in these cases, which means when we finally interpret this into our monoid structure, we're not doing those combines that we would have done if we just sort of interpreted immediately. If we interpreted it with the type class instead of first combining it with our free structure. So that is one of the potential use cases for free structures, is that you can build this tree, you can analyze the tree, you can optimize the tree, and then you can interpret it later on. And you can also take this tree and interpret it in different ways that you wouldn't be able to, if we just combined these as ints the first time, then all we're getting back is, I think we've talked about this a little bit last time, but if you look at the signature for the normal monoid, if we use the monoid as a trait, if say we had a monoid trait for a person that did something, what we would get back out after all of this composition is just that final combined person, whatever that meant, or just the final combined int. We lose the structure of the composition, which if we use a free structure like this, we preserve this structure. And we can ask additional questions like, how many values did you combine? But you don't know that if all you have is the residue, the final result. And it's hard to maybe imagine some concrete cases where that is useful, but it is actually, it's quite useful. I think last time I mentioned you get to suspend this, you get to suspend interpretation, you get to delay it, and you get to use that information to interpret the same structure multiple ways, which could save you some time. Yes, cool. I should make one more monoid instance, by the way, which is the, let's see, implicit def Freemonoid monoids, which would, I guess, take an A here. So yes, obviously you can have a Freemonoid is a monoid. It's the whole point of it. And it's basically just the combination of these things. Why is that sad? That shouldn't really be sad, is it? I must have screwed up something. Freemonoid. Oh, these should be. Freemonoid A. Monoid Freemon. What is this? Freemonoid of A. I probably have screwed something up. What have I done? Oh, I think it's because this is, Oh, this should be a monoid. Oh my God. That's why. Okay. Freemonoid A. What have I done here? I've done something bad. Probably confusing myself.
I got kicked out of the IntelliJ. So.
Found free.monoid of Freemonoid A required. Oh, yeah. Okay. This is just, I just did not parameterize it. That should have been way simpler than it was. I screwed up every type annotation.
It's always simpler in retrospect.
Yeah, I let Copilot run it for me. I'm offloading too much of my brain to Copilot. Okay, so it's really just the Freemonoid monoid. The monoid instance of a Freemonoid is really just doing the AST structure, right? So it's Freemonoid.combine A1, A2. So this really shows that that's a direct ASTification of the trait. We're calling these functions into the trait, which is a kind of a cool thing that you can have the type class instance of the free structure and whatever. Pretty fancy. So now we could, if we wanted to, of course, fold map our free, where'd it go? We can now fold map this back into another, I could say Freemonoid.value and A, and we've basically gotten, oh, I need to say that this is a Freemonoid of person. And there we go. Now we get to sort of do the identity function. And maybe this, Adam gave a great rule for folds last time, where if you call a fold passing in the constructors, for each element, you get back the same item that you started with. You basically get the identity function. The same thing holds with this, whereas if you've done your free structure correctly and you call fold map, you can call whatever your free structure dot, lift function is, whatever just takes a normal value and puts it in that free structure, and it should get you back basically the identity element, or the identity function for that structure. So we've basically gotten the same thing back, which is cool. Or we can do other things. We can reinterpret every person if, let's say, let me do this to make this a little more interesting. Case, person, name, age. I could say if age is greater than 29, then we're going to say, oh, identity element, yes. Otherwise, we can say Freemonoid.value of the person. And what we've just done here is we're basically going to we've removed John, or we can remove Adam. We can, sorry, Adam, we can delete people by reinterpreting it into itself, but sort of mapping particular values to values like identity. Okay, pretty fancy. However, there is something a little interesting about this. I'm not sure, has anyone ever heard, a statement that goes like, the blank is the Freemonoid or something like that? Does that ring a bell? I wonder if anyone has heard. Oh, list, yes, great, exactly, yes. So you might have heard that the list is the Freemonoid, but this is not the list. This is a Freemonoid thing. This doesn't quite look like the list. And that's for a couple of reasons. I actually like this structure because for the longest time I had no idea how the heck is the list the Freemonoid. Like, what is the pattern here? Because I like this because it's a direct ASTification of the trait, and it's this repeatable pattern that you can follow for any trait and make your own Freemonoids. There is one problem with this because I didn't mention one law that does also exist. So there's the left and right identity laws of a monoid. But there is also this associativity law, where this binary operator has to be associative. So if I do ABC, that should be the same thing as, if I do AB and then combine that with C, it should be the same thing as first combining B and C and then pre-combining A. So the association doesn't matter. In this case, we can kind of show that technically the values that we get do matter. So let me say free and free 2, and I will associate these differently. I think this top one is going to be the default that we got, but so yeah, I'm doing A, B, and then C, and here I'm doing B, C, and then A. And we'll take a look at these structures. And if we see here, these trees are slightly different because these nodes are combining them on the left and right side. If we use FoldMap, none of this matters. This doesn't really matter. This is all okay, because once we fold it into something, let me fold it into that first version that we had where I turn everything into an int. So I'll just get out the age. This is going to be the same result for both structures, free and free 2. Because even though our associativity is different in this tree structure, it's just a suspended operation. And once we interpret it into a monoid, as long as that is a lawful instance of a monoid that we're using, in this case, the addition monoid is, it will have those laws intact. So, and actually, I kind of like that about this. I don't know if there is a rule that says the free structure itself has to follow these laws. Technically, free 1 and free 2 are isomorphic to each other. So they're associative up till isomorphism, I guess.
Yeah. Another way you can sometimes think about it is you can control the operators that you expose on this data type. So like, even if you look in Zio, like there are a bunch of operators, like a bunch of data types, like the ones in like Zio test, or even you can think about like the cause data type. So cause is actually represented a very similar way to this. There's a cause.both, and then there's just like a cause.fail. So cause.both is, I think here we've call it our like combine. That's like the same thing as combine. We've got the cause.fail. That's the same thing as like, I think we have it as like the succeed. That's the one that's the carrier, to use the kind of fancy terminology. And then we've got the
empty.
Cause.empty, right? Which in this case is our identity for our little Freemonoid thing here. And so this is supposed to have exactly the structure of, it's supposed to be associative, it's supposed to have an identity element. And so one way you could, and so, you know, you could say, well, I have to like have my data structure in a way that like the data structure inherently reflects that. But the other thing you can do is you can just implement the operators in a way that reflects that here. So like if you look at the implementation of like cause here, there's actually a decent amount of work that went into the implementations of things like equality or hash code to like make sure that if you have the cause dot then A, B, and then you do the C, that's the same as doing A and then B and C. And like if you go to the cause spec, there's actually like a ton of tests that like look at every like possible like combination of these things. So like that's another technique you can have, and you can actually think about that like even if you have like a set or a map in like the Scala standard library, like the reality is the underlying low-level implementation has some concept of ordering, and that's why whenever you print it out, you're going to like see some order of the items in the map, and depending on exactly implementation, it may be one thing or the other. But in the operators, they try to make that not observable, at least outside. Like they may have some qualification of like, look, obviously, if you print out the map, you're going to get it in some order, but otherwise, the order of the map doesn't matter.
Yes. So for instance, technically right now, free 1 and free 2 are not equal, even though according to everything that we talked about with the laws, this should be associative and this shouldn't matter. But we could change the definition of equality for this free structure, as Adam was saying, to make it from the outside, everywhere you're going to interact with this structure, they're equal, and all these laws hold. We could also maybe change the implementation of plus plus, as we already kind of did, to ensure that we always sort of recursed on the right-hand side or something, or on the left-hand side, so that these structures were always regular, so that it would be correct by construction. In this case, though, I mean, since this is a free structure, and once again, I'm not sure, like, I'm not even sure if these laws really exist. Is there a correct encoding in a programming language of a free structure? Does it have to be associative in this way? Or does it, I think it's fine in some way, because once you interpret this back into a monoid, you're getting those laws back. It's going to interpret the same either way, even if there's some wiggle room in this intermediate state. But yeah, we could do a couple of things. One thing we could do, if you recall what the initial sort of catalyst for this is that the Freemonoid is sometimes referred to as a list, but this is not the list. And if we investigate this, we can say, okay, with this one problem where technically this intermediate structure is not associative, but also we can maybe refactor stuff here a little bit. We have these two cases, one of which has a left and right combine, a left to right sort of inductive node, and we have this other case that is this leaf node, and that's interesting. If you've ever made some tree data types before, like a tree of A, you might have, there are a couple ways of making a tree. One is to have kind of just a leaf node where the left and rights are trees, and then the node is an option of an A. Or you could have, that's a weird, I didn't mean to do it, I meant to do case class. But you can have a case class where the leaves are sort of recursive, but it sort of stops recursing. Wait a sec. What am I doing? One sec. Extends. Let me get this to be correct first. Make sure what I'm saying makes sense. Left, right, A. Oh no, because this would have to keep recursing forever, actually. So that's not quite the right one. Maybe it would be that the leaves are optional. That's potentially one way of doing things to get you to the end. Where you have option leaves like this. But you also maybe see one where you have a sort of an explicit empty node, and maybe also an explicit sort of leaf node where you have a value there, value A extends tree. Maybe this example is kind of bad, but the point is there may be multiple ways of factoring out a tree, and that will all technically work. That was ignore that, scratch that. The point I'm getting at is that there's another way of factoring this that will still technically expose the interface we want, but it will work a little differently. And that is to realize that we can actually we still have the ability to combine, because we just need one of these inductive paths to be able to combine monoids together. And we could just arbitrarily say, like, let's just combine down the right-hand side. And we can remove this value primitive, because we can represent the pure primitive as a combination of A and the identity node, which will force us to transform our things a little bit. But that's okay. Let me just make this a little simpler by just saying, so yeah, this combine is going to be a little interesting. So let me rework this. So we're gonna have self match. So if it's identity, if our first one is basically done, then we're going to just return that. But now, if it's A1, A2, we can basically say, well, combine A1 and recurse with the end of the list and keep going recursively in that direction. And for this thing, A1 is basically just going to be the value. So we'll say if value on A1, if value, otherwise we'll recurse going down the end, and we get to remove that value node. So the pure value basically is just this now. And it might be worthwhile at this point to make just a value constructor that is a Freemonoid of A. And this would now be combine of value and identity. And we might have to make some changes down here. So these will just be all value. Cool. And now if we run this, I think something's not going to compile, because this is going to have to be A1 plus A2. So now if we do this, we'll actually see that, oh, they're equal to each other now, even though so now we've made our data structure associative, because when we combine, we're always going to sort of be associating to the right, because we've made our plus plus method a little more clever. And if you look at what we just done, I should probably go up here to this method. And really, this is the head, and this is the tail, right? This is the head, and this is the tail. And we could really rename identity at this point to nil, and combine could be renamed to, colon, colon, or cons or something, right? So this is the list now, essentially. So that's why they say list is the free monoid, because it is sort of a slightly factorized version, more compact version of the type class, which also preserves the associative rule even in its free form. But it can be a little, weird. For a while, I knew, list is the free monoid. I had that mantra in my head, as many functional programmers do. But I didn't know why. I mean, you can call these methods on it, and it was a monoid, and you could put values inside of it. That made sense. But I kind of like the encoding, at least pedagogically, of just translating a type class into an AST, because it really makes it sort of clear and repeatable, this pattern. And then after you do that, you can figure out, are there clever ways of making this more optimal, faster, preserving the laws even in its free structure state, anything else that might be desirable. But that's why if you look at the sort of the definition of fold for a list, it literally is an ad hoc monoid. Like if I go to, not this list. Well, actually, no, this is our list from last time, right? Like this is essentially a sort of a strange version of monoid, where it's not, A and B are different, but it's essentially the structure of monoid. So yeah. It's kind of cool. I don't know. I feel that's pretty fancy. Any questions before we keep plowing ahead?
We are good here.
Okay.
Yeah. It's, I think it is, we just forgot the specific structure of doing our combining, and now we just know it's one F. We just know the order. We don't know the order we combine anymore.
Yeah, and so that could be useful in its own right too. I mean, maybe this is technically more lawful as the free monoid, but that idea of being able to perfectly mirror the AST is potentially more useful for if you do care about the exact order of operations and the associativity that they were called in and all that stuff. That preserves more information about how you called these structures.
Yeah, it's right. It's probably a little more translatable to other things you may want to do, where you're just trying to represent some operation you're doing as a data structure so you can do things with it later. You're not necessarily trying to satisfy these very specific laws.
Yes. Though I think, but perhaps there's probably some more law-based equational reasoning-based approach to defining what a free structure is. And obviously it's like a term from category theory that is very, very specific, that involves a free structure is left adjoint to a forgetful functor or something like this. God help me. No, I want to know what that means. If anyone knows what a forgetful functor is, and adjoints, adjunctions curtain me. They're on the to-do list, but I don't quite understand them yet. But anyway, I feel like hopefully this is a more digestible way of understanding them. And yeah, just because something isn't lawful doesn't mean it's not useful. Though laws tend to help in certain ways. If it's good to know if certain laws exist and you can rely on them. And it's good to know if they don't exist, but if you don't need them in certain cases, then that could be really useful. So having that other version that we had, which is just a pure AST version, is very useful, even though technically that structure itself we know is not associative in its combine operation, because it has different structures of trees you're going to get. It's still useful in some situations and easier to write sometimes because you don't need to cleverly flatten it. And it's more straightforward of an encoding. Both useful. Everything is useful. It's just all trade-offs all the time. Okay. I'm not sure if there's anything else I'd like to talk about the monoid yet.
We've covered the monoid quite extensively.
Yeah. So that's clearly you didn't have enough time to do that last time and get into an actual use case. But if you do go back and watch that video, which I will make sure to upload shortly, there was an extensive explanation at the end through a really maybe too complicated use case of where this idea of preserving this in-between structure, this unevaluated trait, which is this free structure, can be tremendously useful. I mean, why are lists useful, right? They're very useful in many situations, and there are other shapes that you can sort of create and use. But maybe I'm not sure. There's a couple ways we can go. We can talk about how the free monoid is basically the same thing, and the free functor is basically the exact same thing. Yeah, let's do that real quick. Let's make a free monoid real quick, and then we'll get into other a free monad real quick, and then we'll get into other things. So monad. So monad is parameterized by this higher kinded type. So it's a pattern on not values, but higher kinded values. So wrappers of some type, technically covariant wrappers, but I will leave that off for now. And they have a few elements are involved in the pattern. First, this method, sometimes called pure or succeed, something that's going to just take a normal value and put it into that container. And then there's flat map, which if you have a value in a container and a function from from whatever the value in that container to another container of a different type, you're going to get back a container of that other type. So it'll essentially call the function on the inner value here and return the result of that. It's map and then flatten. Essentially, there are other ways of writing this, but just let's stick with this one for converting this to our free structure. Okay, so we're going to take the same series of steps here. Going to make a sealed trait. Going to call it free monad. In our little series of steps, which I might have deleted, no, they're here. Okay. First, we're going to define a sort of an ADT for that interface. And whenever we refer to the sort of the type parameter, we're going to instead replace that with the free structure itself. So an inductive call. And then we're going to have a special carrier node for that type parameter. And so now the type parameter used to be A, but now it's this container. So it's going to become a little stranger. So we're going to need to parameterize this by both our container type, but also a value that it contains. Okay, and now we can move through these steps. Copy these here. So first would be pure. It's pretty easy. This would take a value A, and it will extend. And it will extend free monad f of A. Oops, I should probably give this an F as well. Great. So that's that one. And then the next one is flat map. Oh gosh. All right, so we have an F, an A, and a B. The value actually, because that is the type that is this container here, this is going to be a recursive call. So it's going to be a free monad of f of A, and it's going to then take a function from that A to a free monad of f of B. So that's kind of the rule. When you have a type that is the type parameter, that's when you, in your little signature here, refer inductively to that container type. Okay, cool. And then our last rule is to have a way of lifting a value of this container type into the free monad structure. So I can call this value. Maybe I should have called it lift before, so it could all be consistent. So yeah, maybe I'll just replace. Oh, I removed value. Okay, so let's pretend I called it lift.
Seed, yeah.
Yeah, I factored it out. So let's just call this lift now and pretend I called it lift earlier. Great. So this would take an f of A and extend this into a free monad of f of A. Perfect. Very fancy. So that's basically those same rules again. We converted our AST into a sealed trait with a little sidecar for a normal. And now we can create, nice helper methods. So I can make a function called pure value A. I guess we do have to know what thing we're turning this into ahead of time. Maybe that's unfortunate. That doesn't make that too useful, actually. And we can also have a method called flat map of B, which will take let's just let this do it. Come on, do it. A to free monad of, there we go. Okay. And we create a free monad dot flat map of self and F. And that's basically it. I'll make a lift function as well. F A lift. Cool. It's really not, we don't really know what this is good for yet, or how to use it. But we followed the rules that we had so far. And the next thing we could do to just keep following the rules without really investigating why have this at all would be to create that FoldMap method, right? Which basically we needed a way to go from, let's look at the structure of here. We had a way to go from our parameterized value, our A, to some summary value, Z. And then we had an instance for that Z value. The only problem with this is that our parameterized value, in this case, is a higher kinded type. It's a type constructor. It isn't a value. So we want a function not from f of A to f of B, but we want a function that goes from like our f to some G. Yeah, it's about to get slightly complicated. Unfortunately, that's not going to compile, but we'll just write what we want to exist. And then we want a monad for G. That's basically the way it would look. I don't think this will compile at all. Yes, it's going to say f takes type parameters, duh. F takes type parameters, you dummy. And that's why we're going to instead use a squiggly arrow. And now everything is happy. Unfortunately, that's not syntax either. So there's this concept known as a natural transformation, which is just basically a function like this, the thing that we want, which is going from some functor to another functor without caring about the values at all. But of course, you can't really write that with nice normal type signatures in Scala. So instead, you end up making a natural transformation trait. So this is kind of the trick we used yesterday as well. When the Scala type system doesn't let you do things, you tend to make traits instead. And this allows you to write a signature like this, which is a natural transformation from a functor f to a functor g, is basically a functor from f to g for all A. So irrespective of the contents of that functor, you can transform them. So one example of this would be an implicit, I guess I don't need I could make an implicit one, I guess. Implicit val, like option to list natural transformation. And we can just call toList on the option. Because for any option of A, you can turn it into a list of A, right? If it's none, you do nil, and if it's some, you do a singleton list. And you can go I can't quite, I guess you could go the other way as well, though you will lose values. So that's an example of a natural transformation. But it's really just a mapping between functors. Yeah, that, I hope that makes sense. And sometimes you'll see a type alias here, type ding ding, and then it'll be f, g is a natural transformation from f to g. Cool. So that's basically what that means. So if you have a natural transformation from f to g, so a way of transforming this f type that you have in here, which remember is going to be in our node here, into some g, and you have a monad instance for a g, then you can get back a g of A. How? Why? How is that possible? Well, because this monad instance is basically the syntax tree that we've created. So we'll just translate pure to being the pure of the monad. We'll translate flat map to being flat map of the monad. Oops. Let me write this myself because the value is in fact another free monad. So we'll have to fold map again, fold map with f. And then that's going to get us back our g. And then we're going to give it the f here. Oh, fold map. I think this is okay. I think it's just IntelliJ being confused. I could be wrong. Let's see.
Yeah,
and then lift is going
generalized algebraic data types here, because in the flat map, the type of the inner f is different than the type of the outer f.
Yeah, I might need to cast some stuff because yeah, technically val GA is going to be value. Yeah, because it's an f of any. Fold map f. What does this get us back? Yeah, it's sad.
I think if you apply it directly, it's smart enough to know those two are the same. But I think if you do it through a function like this, it may not be smart enough.
Yeah, so I might need to define this elsewhere, or I could just trick this. This isn't this thing. F is a function from nothing. Oh wait, no. That's my fault because this needs to be G here. That was my fault because I named this F up here. That's the FG function, and this is the F in here. So yes, I'll make this. This is our natural transformation, and then I can call GA dot flat map. Of F. What is this type? G of any. Oh yeah, that technically should work. Oh no, monad dot flat map GA F. GA F. Yeah. Oh, which gets us another free monad. Oh no. Yes, I think this is another step I need to take in here. Let me see if this can work. I'm not sure if that's going to compile. Okay, there's complicated stuff here. All right, never mind. Let's ignore that. This bit here, I don't want to struggle too much with it. Hopefully I didn't screw something up. I mean, I definitely screwed something up because yes, what we're getting back is when we call. Okay, on the left-hand side, we have a free monad from F of FA. Free monad of F any. And if we call that, we can transform this thing into a G of A. But then we have this function from F to a free monad.
Don't you just need to do lambda?
Yeah, let's see what we can do. So the problem here, in this case, let me pull this out. Value 1, this is going to be a G of that in-between value. I wonder if it's because it's just losing the type of that in-between value.
Yeah, I think that's right.
Or no, because this value needs to be converted as well into a G of any. Okay, and that should be G of.
The value is just F of A, right?
FoldMap. Oh yeah. Wait a sec. So that'll be. There we go.
Yep.
Ah, it works. Okay. Yeah. I'm sure It's confusing. It's confusing here.
Yes, we're very abstract here.
Yes, and I'm actually I just made changes until it compiled, but so now we can inline that again and make it beautiful. Okay, but the point is that this is crazy complicated looking and scary and horrible. Let's go back to the simpler, happy version, which was that we had some AST that represented a monoid structure and then also allowed for an A to ride along. We could collapse this into any monoid Z, so long as we can go from our A to a Z, right? Because we may not have a monoid instance for A, but if we turn it into a Z, for which we have a monoid, then we can, at the leaves, translate that A into a Z, and then for the rest of our AST, just translate that into using the structure here. So the same idea applies to the free monad. We have some value F, some higher kinded value F. So some type constructor, any functor, technically, is the word here. And as long as we have a way of translating that into some other thing G, our functor F, which may or may not be a monad, into a G that is a monad, then we can basically translate this AST. At the leaf node, we turn that core value from an F of A into a G of A, for which there is a monad, and then we just basically translate the AST into directly calling those structures. And we have to do a little bit of recursion and whatnot. But besides that, yeah, this is the worst part right here. But it's basically just running our abstract syntax tree in the monad for G. And we can simplify this by like say that okay, if we had a monad for F, we wouldn't need to translate this into G, we could just run it directly. But the nice thing about these free things is that the value that you have in here doesn't necessarily have to conform to the type class that it represents. And what is this good for? Well, really nothing much except more than intellectual exercise in this case. It has been used to represent effect systems. There's some clever ways you can use it, but that may or may not be obvious by just looking at the structure here. It just happens to be that basically this lets you add to any functor F monad-like capabilities, so sequentiality and whatnot. And it lets you sort of have your functor as some separate entity that's nice and clean and unrelated from the monad structure. But really, the way easier thing, instead of doing all this and writing this from scratch, or even using a library that already gives it to you, the thing I'd recommend, why I really generally don't use type classes at all, is because if you understand what you are going for, the operations that you want, the laws that you want, you don't need the type classes. The type classes just let you reason about them generically. If you have a thing, you can just add, some combine operators and do them monomorphically without type classes. You never need to make a monoid instance for thing. And you don't need to make a functor instance for thing or any kind of instance for thing. One sec. Instead, what you do is you just write the methods on that thing, and you know the patterns, and you know what you want. You know that if thing contains A's or produces A's in some way, then you're going to get methods like map. Then you might be able to get methods like flat map. You're probably going to get a method like zip and zip par and all these other sorts of constructors. If thing can fail in some way, you're probably going to get methods like or else. We've talked about this before, but I find understanding these patterns and maybe the signatures and why they appear is so much more than understanding the fancy names and maybe the laws that they hold. Because it's possible, and I experienced this myself, to know all the words, to know all these type classes, and to not really know what they really mean, to know what they're good for, or how to use them without having the type classes, which I find to be way more beneficial and useful and easier to write and easier to read. It doesn't take much lines of code. I don't really gain anything from creating a monoid instance or a monad instance for this thing generally. But I do gain from realizing that, it produces values of A, and therefore I'm going to have these methods and I could follow these patterns that I've boringly followed before in a way that doesn't add needless abstraction. And I went for a long time when I was a Haskell fan, not even really being able to do that, instead of just only being able to think in terms of type classes. But yeah. Okay, we got 10 more minutes. So Freemonad, it's the same pattern, literally. It's just that there's a little more complexity and ugliness. And we had to mention this idea of natural transformation. But really, it's just this idea of representing any kind of trait as a data type. And then if that trait happens to be a type class, then you can use that type class to interpret it. But you also don't have to have a type class. You could just, because a type class is nothing more than a bundle of methods, you could just have an ad hoc instance of that type class. Or maybe the thing isn't really any one type class. Maybe it's a combination of type classes or just something else that you have. Then just accept the functions that correspond to the trait directly, or whatever your AST is directly. And that could be very, very useful. I will show one example because we talked about it at the beginning. No, not in here. Oops, not Zio. But inside of the parallel for implementation, one instance that I used actually of a free structure was to test this thing. Where did this go? Parallel spec, yes. So I wanted to be able to test this in a way that made sure that it sort of parallel for would parallelize maximally the for comprehension. And I didn't really want to run it through an effect system. I could make a version against Zio, and I probably will. There's probably some clever ways I could do that. but that involves, probably going to have some, use the clock, add some delays, make sure that things are sort of chunked in the right order. I kind of wanted just a pure way to make sure that this thing, this parallel macro rewrote the for comprehension to be parallelized just in a structural way. So what I did was I made a free parallel structure, which is basically a free structure, sort of, even though it doesn't necessarily correspond to a traditional type class. It's
which goes back to exactly this idea of using this declarative encoding approach and just everything you need to do, make a data constructor for.
Exactly. So I made a data constructor for these. So I have my zip par, which zips a left and a right parallel together to get a free parallel of a tuple, a flat map. So it's a little bit of a combination of a free monad and a free, I guess, applicative would be the fancy word for it, but really it's just what I needed. And then I have this sort of value that the succeed node that allows anything to just become a free parallel structure. And so that's basically what this thing builds. These will build free parallels. And then I can execute these things, or I have this method called trace, actually, which runs this free parallel structure, leaving behind another structure here that represents the path that it took. So you have sort of these nodes that represent sort of the trail, the mucusy trail of the execution of that free structure. So if a bunch of values were zipped together, I'm going to get the zipped node. If there was a flat map, I'm going to get the thing that was flat mapped and its result. So I get the structure that represents the history of my execution, which allows me in my specs to make assertions that parallelizing this for comprehension will essentially just zip together the values 5, 10, and 20. It's going to execute these three things in parallel. And I can also get the result, the pure result of that computation to make sure that the sum of those are 35. For this one, I'm going to make sure that it's zipped together 5, 10, and 15, and then executed this next effect, because this depended on the previous ones. So these are just some fancy constructors for basically constructing a flat map node. Zipped just constructs a zipped node with multiple values. And so this version, actually, this trace entity isn't really even technically a free structure in the same way. It's just an ADT, but it's a pretty convenient thing that I've used in a couple of libraries to in the sort of this. I'm also using it in the assert true implementation in sort of a different way for tracing execution. Just as you interpret one of these data structures, you can generate a value that represents its execution. And yeah, it turned out to be a kind of neat way, I thought, of testing purely this thing that's kind of doing complicated stuff behind the scenes. And just to show off the implementation of trace. So let's look at the trace implementation of, let's say, the succeed node just generates a trace value, which is sort of the leaf node of the trace, pretty boring. And we need its actual result in order to generate the next traces. The flat map version will, remember, this has a free parallel on the left-hand side, so a free parallel of A, and then a function from an A to a free parallel of B. And so I call trace on the left-hand side, getting back the trace of the left-hand side and its result. And that allows me to call the function on the right-hand side, which gets me back another free parallel, of which I can call trace on, which will get me the trace of the right-hand side and its result. And then I can create a combined trace, which is the left-hand side, and then the right-hand side, right? This other trace node, which represents the flat map. And then I can tuple that together, the trace and the result. And then in the zip par case, I basically just call trace on either side, zip together their traces, which I have a little fancy thing to make sure I chunk up the values, which is nice. And then also get the result. So yeah, that trace simple does two things. It both gets you the result, but it also returns this sort of mucusy path of breadcrumbs that represent the path of computation, which is really, it was really simple to implement, and it was useful for this test. And I don't know if that's a pattern, if that quite fits in with free structures, but that's the fun thing about free structures. You can just reinterpret them in many ways, use them to run to summary values, but also run them into sort of tracing the path of their execution. Other free structures, yes, into itself, right? As we did very briefly with the monoid. Yeah, and it's pretty cool. there's one, let me see if I could find it. Free group Haskell advent of code. Let me see if I can get this article. Alchemical groups, yes, I'm just gonna post this in the chat because this one was kind of interesting. It's about an advent of code problem that someone used a Haskell free group library to solve, which I find Haskell libraries like this tend to obscure what's going on, but maybe now that we talked about this, it will make a little more sense, but maybe we can go over it in the future. But it's kind of a nice, convenient or cool use of a free structure in an advent of code problem. Well, we made it. We made it. We talked about free stuff. That's all I know about free stuff. Thank you for listening. Any other? How's everyone doing?
I think people are doing okay.
Jazzed. Everyone's going to use free structures everywhere.
Good.
All good.
You landed the plane.
Okay. Well, that was fun. Yeah, so we don't tend to do super FP things. We don't talk about natural transformations or things too often. So we thought we'd have a little bit of that fun and try to show some useful ways of using them. So yeah, we'll probably get to more practical things next week. We will decide, but if anyone, as usual, has any thoughts, please open an issue on our Zymposium GitHub project, and we will see you around.
Thanks, everyone.
Thanks, Adam.